It is a great pleasure to welcome you here. And I'm Mike Walter. I'm the director at the Earth and Planets Laboratory. And tonight, it's my pleasure to introduce our speaker, Alan Boss. Alan has been a staff scientist at Carnegie Science for 43 years. And yes, claps. I think that's entirely appropriate. Most of that time at the Department of Terrestrial Magnetism. And a few years ago, we became the Earth and Planets Lab. And if memory serves me, I think Alan had a lot to do with coming up with that particular moniker, which in many ways describes more appropriately what Alan does, especially the planets part. So Alan has spent a career really wondering and trying to figure out how you start with a bunch of gas and dust in space and end up with a solar system like our own, or an exosolar system, a star with planets circling around it. And he does that a couple of ways. So Alan is an astrophysicist, and he uses theory to make computational models of how such a cloud might condense and collapse into a star, how it evolves, how it mixes, what the thermal structure of it is, how planets, especially giant planets like Jupiter and Saturn, how they collapse and form. But it doesn't end there for Alan. Alan's also an observer. He's been a leader in what is the Carnegie Astrometric Planet Search Project for many years. And that kind of leads into, I think, what we're going to hear about tonight. Are there planets like Earth around other stars? Part 2. And you're probably like, why is it part 2? Well, in 2006, and I think it was the first ever neighborhood lecture, that was part 1. So this is the sequel we've all been waiting for 18 years. Was anybody here at part 1? Yes, Alan was here. We have some other folks that were here as well. So Alan, we're all very pleased to welcome you here tonight, and you can take it away.
Well, there you go. Okay. Well, thank you. Thank you very much, Michael. And let me start off by repeating his thanks to all of you for coming out on a rather chilly, blustery December day. This is not the type of night I would like to be out. I'd particularly rather be home, in a nice warm bed or something watching TV. But here I am speaking to you all because I want to tell you about what's going on in the last 20-odd years in the search for worlds around other stars, in particular habitable worlds. That's our short-term phrase for Earth. We don't really mean anything exactly like Earth, but we're looking for something which has maybe something like the mass of Earth and is orbiting around its star at a distance where the amount of light it gets from the sun would allow for water to be liquid on the surface, which we take as sort of the most basic astronomical requirement for a habitable planet, because all life on Earth depends on having water. There may be other forms of life perhaps in the universe, but we assume let's at least look for Earth-like life, and so that means water. Okay, so back to part 2. Mike sort of spoiled already, but I'll tell you what the real reason is why I wanted to go with part 2 is because I kind of like these old crazy Charlie Sheen movies, he was pretending to be Rambo. So I figured here's my chance to go do a part 2 thing. But here literally is the introductory slide from 18 years ago. We had a slightly different logo back then. We had Andrew Carnegie, our benefactor. And there's the same talk as neighborhood lecture series at the beginning of the season, as Michael pointed out. So why is it so hard to actually accomplish the search for other Earth-like planets? Why can't we just take a telescope and look at stars nearby and pick out the points of light that come from the Earth? Well, here is the real problem. The problem is quite simple, that even though planets can be reasonably bright, for example, Earth here, showing its amount of light that it gives off as a function of wavelength, where visible light is around here, short of 1 micron. This is reflected light from Earth, showing that Earth reflects about 1/10,000,000th of the light that the sun gives off. That means it's essentially the same brightness as a 30th magnitude star, which actually can be seen. The Hubble Deep Field took pictures of 30th magnitude galaxies. If you just take a 2.4 meter telescope, point it in space, and wait for a couple of weeks, takes lots of images, you can pick it up. That's not trivial either, of course, but at least it could be done. The problem is it's faint and it's right next to something very bright. That's the killer. How to separate out the glare from the star from a little bit of light 10 billion times fainter right next to it. That's why it's taken quite some time for us to be ambitious enough to try to propose how to detect Earth-like planets by direct imaging, by just taking a picture. Instead, the real progress that's been made primarily is through learning that something we learned in elementary school is not right. The Earth does not go around the sun. The Earth and all the planets and the sun go around the center of mass of the entire system. So if here's the center of mass and the sun wobbles around this as well, the wobble is mostly caused for our solar system by Jupiter, which is the most massive planet. Jupiter is 1,000 times less massive than the sun. So the center of mass basically is 1,000 times closer to the sun than Jupiter. It's like a teeter-totter. Or to balance out, sun only has to go 1/1000th of what Jupiter has to do to balance things out. And so for the case of Jupiter, that actually means, because Jupiter is out at, let's see, 1,000 times the radius of the sun, it's actually the radius of the sun is the size of the circle that the Earth wobbles over with a 12-year period for Jupiter. So if you could look at our sun from nearby, you would see the sun wobble around every 12 years, a little tiny circle equal to its own radius. Seems physically possible, but that angle, even from a nearby star, like 10 parsecs or so, typical nearby star distance, 33 light years, that angle is 1 milliarc second for Jupiter making the sun wobble. 1 milliarc second is actually a pretty small angle for all of us human beings. That's basically the size of a dime 1,000 miles away. But astronomers think they can measure it. I myself have tried to measure it. Can't say it's been too successful so far, but because I've been trying to do it underneath the Earth's atmosphere, but it is a challenge that astronomers have been working on for some time. And so the story really begins when you go to the study of Barnard's star. Barnard's star is this seemingly bright star here. It's not actually very bright. It's a red dwarf. It is actually the fourth closest star to our solar system. Two closest stars, Proxen, which you'll see shortly, and the Alpha Cen binary star system. And then comes Barnard's star, fourth closest star. It's at about 6 light years away, 1.8 parsecs. And you really want, if you're looking for this wobble, you want that star to be close by because it makes the wobble look that much bigger, right? Also, Barnard's star was a great star to study because it is a red dwarf with much less mass than the sun. It's only 1/7 the mass of the sun. So that means it's going to wobble seven times larger than the sun would for a given planet. So Barnard's star is a perfect target to look for an astrometric wobble that could be caused by an unseen planet. So the story then begins really in 1937 when an astronomer by the name of Peter Bandykamp became the director of the Sproul Observatory at Swarthmore College. And he started studying Barnard's star the next year, 1938, took plates of it every year. He had generations of undergraduates measure the place to try to see exactly where the star is with respect to other nearby stars. And after 25 years of data taking, he finally was ready to publish a paper on it. You have to be a very patient person to be an astronomer. 25 years to get one, you would have lost tenure certainly if he'd not already been a professor at the university. So here's what he found after 25 years of data. He found evidence for what he claimed to be a 24-year period in 2 different directions on the sky. So right ascension declination, just think of it as X and Y. And you can see he sort of repeats these points here are the same as these points, just sort of assuming that it's a periodic orbit, it's going to keep on going indefinitely. The size of the point tells you something about how much confidence he had in it. So these guys, large points, he had a little confidence in, a little bit more error on these here. But if you fit the curve to this apparent wobble on the sky in 2 directions, that could be fit by a planet with a mass just 60% more massive than a Jupiter. And for this star, it would be orbiting with the 24-year period out at 4.4 times the Earth-Sun distance instead of 5.2 times for our Jupiter. So that all sounds quite like our Jupiter. The only odd thing perhaps is this little bit of eccentric orbit. With a circular orbit like our Jupiter is primarily, it would be a nice sinusoidal shape. So it's a little bit eccentric, but otherwise perhaps not too surprising. But these are hard measurements to do. These are done on photographic plates with, as I say, undergraduate students trying to measure them. And they're trying to measure things on the plate to what plus or minus 1 micron as a scale on the plate, which turns out to be 10 milliarc seconds on the sky. But this became the accepted version of, well, there is a Jupiter-like planet out there around at least one star. Went into the textbooks, classic textbook I saw as an undergraduate, George A. Bell has, yep, we have one Jupiter out there. That's probably okay. So that was fine. But then along came a colleague of mine, George Gatewood, who began to do his thesis work. And his advisor said, why don't you go back to see if Van de Kamp's planet is real or not? So he went to look at plates taken by a different telescope at a different observatory. And instead of having it measured by undergraduates, not to denigrate undergraduates, we had it measured on a brand new, newfangled plate measuring machine over here in DC at the new Naval Observatory, where they were measuring their old plates. And they decided, let's have a machine do it and automate it to control the errors. So after analyzing those plates, George Gatewood and his advisor, Heinrich Eichhorn, came up with this set of data, where again, the larger points, these are repeated again. Larger points mean you should believe them. The little ones you shouldn't believe quite so much. This you should not believe at all because it's actually a speck of dust that occurred when I converted my slides to PowerPoint. But Peter Van de Kamp would have claimed that was a good point, but no, that's actually dust. So clearly, I mean, there's one point here that doesn't look too bad, but if you ignore that one, nothing else, and these don't look very good. Nothing fits Van de Kamp's orbit. So Gatewood and Eichhorn very gentlemanly said, we see no evidence for the wobble. That's all they went. They didn't try to dump on Peter Van de Kamp. And so at this point, we lost our one extrasolar planet. Field sort of fell into a Rip Van Winkle sleep for 20 years. And so things took a while to get started again, although in the beginning of 1988, I actually started serving on NASA committees charged with trying to figure out how to look for planets. So I've been in this business for 36 years, and I'm still haven't quite finished things up yet, shall we say. It's been my 43 years at Carnegie. We're still working on it. But the key thing is that there are other ways to try to find planets besides astrometry, which is pretty tough from the ground. You can also look for the wobble that's induced by the star going around the center mass of the system as measured by the Doppler shift of lines in its spectrum. That is, if you're looking at a given line in a star spectrum, and the star is moving away from you, that line is red shifted to longer wavelengths. When the star is on the phase of the orbit moving towards you, it's blue shifted. So if you actually watched a star has a planet around it and looked at the spectral lines at very high spectral resolution, you'll see them shift back and forth with the period of the planet. In the case of Jupiter, Jupiter makes the sun wobble back and forth with plus or minus 13 meters per second, depending on where it's going. That's 30 miles an hour. So you think, well, 30 miles an hour, that should not be hard to detect. I mean, if you drive on Connecticut Avenue 30 miles an hour over the speed cameras, they're going to nail you. You'll get a little letter in the mail about that. But the problem is it's 30 miles per hour or 13 meters per second with respect to the speed of light, which is huge in comparison. That's like between 1 part in 10 million and 1 part in 100 million. So you need a very precise spectrometer to measure that kind of very small shift in wavelengths. Well, a number of groups were working on that at this time in the 1980s, and the ones that struck pay dirt first was a Swiss group, Michel Mayor and Didier Queloz. They had just developed a new spectrometer at the Hall Provence Observatory in southern France, a modest 2-meter telescope. And their spectrometer they thought was able to measure plus or minus 10 meters per second. Jupiters are 13 meters per second, so they figured, let's see if we can find some Jupiters. So they studied a sample of 100 stars. Of 100 stars, they only found one that wobbled, 51 Peg, which is a solar twin, very much a solar-like type star. And they took observations over several years while the star was visible. And you can see the error bars are sort of plus or minus 10 meters per second. And they found this periodic wobble, up and down, up and down. Not quite sure what happened this night here. It may have been too much Beaujolais in their night lunch or something. Something went wrong. But this nice sinusoidal curve implies a nice circular orbit, like you might expect. And the amplitude, about 55 meters per second, implies for this solar type star that the planet is about half a Jupiter mass. All right, so there you go. That all sounds good. The only strange thing was this orbital period is not 12 years, it's 4.23 days. That's not supposed to be there. That means its orbital separation is about 0.05 times the Earth-Sun distance, which means it's actually out at about 10 times the radius of the sun orbiting around. It's very close to its sun. It's very hot. It's thousands of degrees Fahrenheit in its atmosphere. It is a hot Jupiter. Wasn't supposed to be there. Theorists like me, we scratched our heads because we were trying to make Jupiters out where they belong, 5, 10 times the distance from the sun. How did this get here? Well, theorists think it had to have formed farther out and migrate in, but that's a subject for a whole nother talk. But the key thing was they made a claim, and I actually was a referee for this paper, believe it or not. And we were in the process of refereeing the paper because a number of us were so amazed by this, we had to raise some serious questions about this for their Nature paper. But Mayor spilled the beans at a conference in Florence in October, and he just went out and said, here's what we found. And the great thing about it was that people then knew about it, and a colleague of mine, Paul Butler, and his colleague, Jeff Marcy, were able to go to the Lick Observatory the next week. They had observing time and look at the same star with their spectrometer they'd been developing, and they could reproduce that same 4.23-day period. So right away we knew that planet was real, and they could ignore the referee remarks for people like me. Paper went and got published without addressing the concerns we raised. So that was really the beginning of the whole field that really started things bubbling. And in fact, in 2019, Michel and Didier won the Nobel Prize in physics, shared with Jim Peebles, the cosmologist, but that is the one big Nobel Prize in our field to date. So we know that method works really well. There is a third method that is indirect, which involves when a planet passes in front of its star by chance. When it transits in front of the star, it's called the transit. When it goes behind, it's called an eclipse. And this produces a measurable dimming of the star's light. It's not necessarily very much. If you're talking about an Earth going in front of the sun, the Earth is roughly 1/100th the size of the sun, which means that the area that it blocks out is 1/10,000th of the sunlight. So it means the sun just dims by a part in 10,000. When Earth passes in front of it, here's what Venus looks like when it passes in front of the sun. This is actually done by an astronomer from Northern Virginia who kindly lent me his own image that he had taken. I mean, that's something which is 100 times smaller than the sun. Very small dimming. If you're a Jupiter, you're 10 times larger in radius. That means you're only blocking out 1% of the starlight. And that you can measure from the ground, actually. In fact, if you have a hot Jupiter, it turns out that for randomly inclined orbits that are out at 10 times the Earth, the sun's radius, there's a 10% chance that one of them should transit. Well, we found 10 hot Jupiters until finally the 10th one transited. It's a bit of a shock. We wonder how come none of these are transiting. The 10th one did it, HT 209458b. And that could be measured, believe it or not, from a parking lot in Boulder, Colorado with a 4-centimeter celestron telescope. No big deal. That you can do from the ground, measure Jupiters. But if you want to find Earths, guess what? Like I just said, it's 100 times worse. You have to be able to measure things to 1 part in 10,000. You can't do that underneath our atmosphere. The atmosphere has too much twinkling. If you've looked out in a bright sky and seen twinkling stars, you know that that's just not going to happen. So because of that, back in 2006 when I gave this talk, we were very much involved in planning a space mission to do the same search, to try to build the Kepler telescope. At that time, we thought it would launch the next year, 2007. Kepler is a relatively small telescope, has a 1.4 meter primary mirror here with a 95-centimeter Schmidt corrector on top, which is a very wide field telescope. It's made to stare at a star and see the transit of a little tiny Earth pass in front. It was designed, its mission specifications were, thou shalt detect 50 Earths. That was how it was designed to be. And it's planning to spend at least 4 years staring at a field of stars in Cygnus, a constellation of the Northern Hemisphere, looking at a field of sky which is 10 degrees by 10 degrees, which is like 20 moons by 20 moons in size, staring at it constantly without ever closing its eyes, kind of like the character Alex in A Clockwork Orange, if you remember that horrible movie. I guess none of you do, so you didn't get a chuckle out of that one. But there's a scene where, well, I won't go into that. But yeah, what Kepler telescope had a blinder which was blown off, And thereafter, it had to stare constantly, could never shut its eyes because you did not want to stop taking data. So it stared at that field of view for 4 years. You want to look for at least 4 years because we're looking by definition for Earth-like planets around sun-like stars, which means it's going to take them 1 year to come around and pass around. So you see one dimming, one transit. Wait for another year, there's a second one. Yeah, let's see if it occurs, the third one, at the specified time. And so if you see 3 transits, you start thinking that must be real. So you had to run for at least 4 years to see at least 3 transits. So that was the plan. Going to launch in 2007. It was designed to have enough precision to be able to detect Earths. At that time, we were really ambitious about doing things in space. We also were planning on building a space-borne interferometer that would measure astrometric separations of stars versus nearby background stars. It's going back to the same thing that Peter Van de Kamp would do, but to do it much more precisely with what was at the time called a nulling interferometer. These are actually 39-meter siderostats, which are just flat pieces of glass, which would have on a 10-meter boom, so giving you the resolving power of a 10-meter spacecraft. And the light would come down, bounce towards a beam combiner in the middle. It uses the principles of constructive interference and destruction to zero out the light from the star, hopefully pick up the wobble that was due to the having a planet around it. There'd been actually a fair amount of work was put into this. In fact, George Gatewood and I were both involved in helping plan this mission. And we just thought it was a few more years off to go. But given them, it's a rather large space mission, it was kind of pricey, so it was unclear what its future would be. But in addition to trying to do astrometry, there's also the idea that, well, maybe we can actually try the direct imaging in space. And in order to do that, you need to have something called a chronograph. Here's the historically most famous chronograph, which is the moon passing in front of the sun. This is what actually an image someone took during this year's total solar eclipse. The moon blocks out the starlight quite nicely and allows you to see the corona. So solar physicists build their own telescopes with occulting disks in front to block out the starlight, and those things are called chronographs. We use the same term to refer to chronographs to look for planets from other stars, because the whole idea is to block out the starlight. And simply having a round stop like this doesn't do you much good because you can see the corona goes right around. And in fact, if you just make a much bigger occulting block, you still will get starlight diffracting around the edge of whatever it is you're blocking. And you can only accept a little bit of that because you're looking for something which is 10 billion times fainter. So you have to have a really good coronagraph design to do that. And to show you the details of that, it's much more, shall we say, complex than simply having a block like the moon in front of it. But people have been doing design work in the laboratory, Jet Propulsion Laboratory, for many years. I was involved in overseeing that work as well. So by 2006, we were planning on launching something called the Terrestrial Planet Finder Chronograph. And so it would have a very high efficiency hybrid LEO chronograph. And the primary mirror was planned to be, you wanted something at least 6 meters in diameter to give you the resolving power in order to pick up something at 1 AU from a solar type star in the habitable zone. But the problem was at the time, the largest launch vehicle we had, the Atlas V, only had a launch fairing, which is the cover that has the payload inside. Its diameter is 4.2 meters. So I said, well, that's okay. We'll just make it 6 meters by 4 meters, put it in sideways, sort of. And then we'll just rotate it around the 6 meters. So we have effectively the 6 meter resolving power, but we can still fit it inside the Atlas V. By the way, Elon Musk's Starship has a launch fairing of 8 meters. So we can imagine someday, if we really wanted to build a really big telescope, we wouldn't have to turn it sideways or wouldn't have to fold it up like you'll see from James Webb Space Telescope. But we'll leave that for Elon Musk and the new administration in NASA, which was just announced, I guess, today. Jared Isaacson will be leading NASA in the future. We'll see how that goes. Okay, so that's where we were in 2006. But in addition, we were really drinking Kool-Aid because we thought, let's even go farther along to building big spacecrafts. Let's build a terrestrial planet finder interferometer. We would now be looking not in optical wavelengths, like everything I've told you before, but out at infrared wavelengths. Whereas you saw from the very beginning, the contrast is only a part in a billion versus a part in 10 billion. Means you don't have to be, you can do a much better job of resolving it. But the problem is if you go to longer wavelengths, you also got to make your telescope 10 times longer wavelengths. You got to have 10 times larger telescope if you have the same resolving power. So this TPF interferometer was planned to be 100 meters long. 1 meter telescopes, 4 1-meter telescopes here, all sending their beam to a beam combiner, which would combine them again through constructive interference to be able to resolve out an image of a planetary system around a star. And the nice thing about TPF being the formation flyer is you could slide these back and forth and really make a nice image. It's called, for the aficionados of the field, it's called filling out the UV plane. If you just have a simple, like the SIM interferometer, you don't really get a good picture, but if you can move the siderostats, or in this case, the spacecraft back and forth, you can get if you take enough images, you can actually get a good picture of what the system looks like. So that's where we thought we were in 2009, and we'd already found a couple hundred planets, mostly by Doppler spectroscopy. My colleague Paul Butler here is responsible for a large number of these, you can see a fair number of different planets. So that we some we expected, some we didn't expect. We certainly did not expect hot Jupiters over here, but a number of cold Jupiters. And there are a number of things sort of uncertain what they are. They're sort of a Neptune, Uranus mass. You might call them, if they're sort of rocky, you might call them super Earths, or you can call them hot super Earths, or wet Uranuses and Neptunes. They're warm enough perhaps to melt their water. But there's nothing quite here yet. And this is largely an observational bias because there are presumably lots of planets down below, but both Doppler spectroscopy and transit timing really are best at finding short period orbits. And so you mostly find things, and also massive objects or larger objects. And so you really populate this area of discovery space much easier than you do this area. So this is where the challenge is to get down into this region here. As of 2006, we didn't have anything there yet, but we did have folks like Paul Butler and Michel Mayor who sort of extrapolated into the unknown, and based on these small number of planets here, said, well, here's how many we think are down here. And they said, basically, we think that each star roughly should have out of every 10 stars, one should have an Earth-like planet. So that's sort of the fraction of Earth-like worlds. They estimated so-called eta sub Earth, it's often referred to as being 1/10 roughly. So here we were. This is literally the conclusion slide, including my funky color choices. We got gas giants, we got ice giants, maybe some terrestrial planets. Eta sub Earth is pretty high. So, hey, we're really going here. Kepler's going to go, SIM's going to go, TPFC, TPFI. Another 1 or 2 years, we're going to have it on the front page of the Washington Post above the fold. So what actually happened? Well, Kepler launched a couple of years late, 2009. It had some rough times. Its costs went up, went about $200 million over its costs. It actually faced the deadly cancellation review where things get canceled at NASA, but it survived it. But it did launch March 9th, 2009. It was a night launch out of Cape Canaveral Air Force Station. I was a member of the Kepler team, so I get to go down and watch it. It's spectacular to see a night launch. And Kepler went out and spent its 4 years studying that field in Cygnus. And when the first targets looked at was a star called HAT P7. This is one that's actually been found by a ground-based survey. So it's sort of a Jupiter size, 1% dip in luminosity. They knew it was there, but we know it's there. Let's right away start just taking good data on this to see if we can reproduce the ground-based results. And of course they could. So you get this very clear transit effect, a little over close to 1% of a dip. But in addition, Kepler could have enough precision that it could actually see the eclipse of the planet going behind the star. So when the planet's right next to the star, you're getting light from the star as well as the planet reflected light. Then you lose the planet's reflected light, and it comes back out again, so it comes back up again. So you could not measure that from the ground, but you could see that quite clearly in the Kepler data, especially when the black points are individual data points, and then the green is a sort of a running average. So that's pretty good. Clearly, it works. But the unsavory aspect of it is that the individual data points and even sort of the grain points averaged out are oscillating back and forth by about 100 parts per million. And they had proposed, when they built the spacecraft and the mission, they were thinking that stars should be pretty much like the sun, which is steady to about 24 parts per million. Turns out the sun is a very quiet star. It misled us. Most stars are more noisy. And so you can imagine if you have a noisy star with noise at the level that you're looking for. We're looking for a part in 10,000. That's how much the star is varying all by itself, without having any planets there. That's made it harder for Kepler to achieve what it wanted to do. In addition, Kepler has these reaction wheels, which are basically gyroscopes, which keep it pointed steadily in space. And if we were shipped with 4 reaction wheels, at the time of shipping, we knew there was some problem with these reaction wheels because another spacecraft with reaction wheels began failing. But they said it's too late to take them out. We're just going to fly them and see what happens. So after a little over 3.5 years or so of operations, 1 reaction wheel failed, but we still had a spare. So we had 3 reaction wheels, which was necessary. We needed to keep pointing exactly the same direction. And then after another couple of months, another one failed. So we were down to 2 reaction wheels, which meant you could no longer steadily point at the same region. So at that point, Kepler's prime mission was over. They continued taking data by some clever engineering, but it could not be as precise as what they were intending it to be. And so that means that Kepler did the best it could, but it did not find any exact Earth analogs. It failed its mission 1 level requirements of you shall find 50 Earths. Didn't find any. It found some that are close, but nothing that was exactly within 1% or 10% Earth size. This shows you the final data release, showing you the size of the planets that they found, where the habitable zone is, either the optimistic habitable zone or the conservative habitable zone here, which optimistic includes a bit of Venus, but sort of hidden behind is the size of Earth. And the points shows that the ones that were detected at the right distance to be habitable around solar type stars, they're quite a bit bigger than Earth and Venus, right? Those are super Earths. So they're interesting, they're great science there. We'd like to know what those planets are like, but they are not quote unquote Earths, which means again, people have to extrapolate from what was known and observed to make a guess as to what the frequency is of Earths, but it did go up quite a bit because they did find a lot of these objects like this, given their observational biases. And so the most recent paper, the final paper by Steve Bryson, published a couple of years ago, estimated ATIS of Earth as 0.6 to 0.8, which is in itself an amazing thing. So basically, if you look up at the sky and see 100 FGK stars, 60 or 80 of them are going to have an Earth-like planet there in the habitable zone. That's stunning. Think of that next time you go out and look at a night sky. You are very well looking at stars that have habitable worlds around them. We don't know which ones they are, but we're sure as hell going to try to find them. So that's some tremendous progress right there. So that's good news. Even though Kepler did not actually find any Earths, we learned a lot about what's out there. There were some other things that happened that weren't quite such good news, though. Every 10 years, the National Academy of Sciences has something called the Astronomy Decadal Survey, where they gather together a bunch of distinguished astronomers to sit down for almost a year or so and battle with each other over where we should spend our money now. Astronomers love to spend money. They always have more money, more things they want than we have money to pay for. I was actually on one of the sub-panels for Astro 2010 that was charged with building space telescopes. We thought maybe $4 or $5 billion to spend. We had proposals for $50 billion worth of projects. We were oversubscribed by a factor of 10, which we could only pick 1 out of 10 proposals. And along the way, the Space Interferometry mission was proposed. They figured we only need another $1.6 billion to finish it. They said, no, forget about it. Just throw away the $600 million. The money that is spent on the TPFs, again, nah, forget about it. We'll do that sometime in the future. But they did say that, well, we will fly you another telescope called WFIRST, Wide Field Infrared Survey Telescope, and it will be able to do microlensing, which I'll explain in a moment. And that does detect exoplanets. And so instead of having these astrometric telescopes or direct imaging telescopes, they handed us microlensing, which is like, who ordered that? Very few people were doing microlensing at the time. So we weren't terribly pleased with that. I got outvoted. I was voting for other telescopes, but my vote did not count as well as other people's because it's mostly driven by the cosmology folks who are trying to measure a cosmological parameter called W. And so this was kind of, and they wanted to beat the Europeans who were planning their own space telescopes. So this name, even though it's a nice acronym, is actually a pun on the fact that they're kind of trying to measure W before the Europeans do. So the inside joke there. The good thing that came along, though, was that shortly thereafter, it turns out the National Reconnaissance Office freed up 2 sets of Hubble-class optics, same size as Hubble, 2.4 meters. It was part of a program that they had ran over budget and over time on, and so they just said, forget about it. They canceled it, like Kepler almost got canceled. And they had these optics sitting in cold storage in upstate New York for years. They finally said, maybe NASA, would you like these? So NASA had a little competition. The only constraint on the competition was, thou shalt not use these optics to look at the Earth, which is what they were designed to do in the first place. It was, basically to look on Osama bin Laden's license plate at the time. And so there was a competition. There were some Earth scientists who wanted to use the optics to look at the Earth's auroras. Good science, but no, you're looking at the Earth then, so you cannot do that. But the astronomers said, well, we got something to look at that has nothing to do with the Earth, so we got the optics. I remember a meeting that Dave Spergel, a Carnegie trustee, held up at Princeton, where we all got together and made plans for let's fly W first on these 2.4 meter optics. We thought, wow, it's free optics, right? We can build this for nothing. Well, wrong. It's costing about $4 or $5 billion to build it, but the idea, it's time seemed like a good idea. All right, so here is that 2.4 meter NRO telescope. And it's been named after Nancy Grace Roman, who you may or may not know, but she was the often called the mother of Hubble. She was the person that pushed the Hubble Space Telescope through NASA and got it built and developed. She lived nearby. She was a good friend of Vera Rubin, who's an astronomer here that founded the astronomy group. And so if it's not for Vera Rubin, I would not be here probably, because she was the beginning of astronomy. And she and Nancy Grace Roman were good friends. In fact, Nancy, if she retired from Goddard, she would often come to our seminars and sit and listen to speeches and lectures, and ask very probing questions afterwards, which often surprised people because they were looking at this gray-haired lady sitting in the back, and suddenly she knocks them over with some really pungent questions. So there was a lot of people got brought up to date quickly on how brilliant Nancy Grace Roman was. I happened to be at a meeting in Caltech this summer about what WFIRST will be doing or what Roman will be doing. One of the nice things was they were constantly heard the phrase, well, Roman will be working with Rubin, because Vera Rubin has her own telescope named after her. The large scale Synoptic telescope, an 8-meter class telescope in Chile, is named after Vera Rubin. Our Carnegie person, we not only have the Hubble, the Carnegie astronomer, we now have the Rubin telescope. And they were talking about how this space telescope will work well with this telescope in Chile, phasing up the observations between the two. So I pointed out to people, the odd thing is Vera Rubin and Nancy Grace Roman were good friends with each other. And so the fact you're talking about Rubin working with Roman and Roman working with Rubin is just, warms the cockles of my heart to know that long after they're gone, people will be saying Roman's working with Rubin. Amazing. Sometimes it's a small world in astronomy. Okay, but what about this microlensing thing? What are we getting for the price of measuring cosmological W? Well, this is the fourth indirect detection called gravitational microlensing. This is something Albert Einstein theorized back in the 1930s. He didn't really want to bother publishing it, but somebody said, oh, go ahead, publish it. He says, it's impractical, it'll never work. He finally published it, and the idea is, in his general theory of relativity, mass bends space-time. And so if you have a massive, if you're looking, sitting on Earth with a telescope watching a background star, watching its brightness, and like towards the center of our galaxy where there are many, many stars, and a nearby, much closer star just passes in front, its mass will distort gravity, and the light from this background star, instead of going off in this direction, will be bent towards you from both sides. And so you'll get momentarily a brightening of the apparent brightness of the star back here. And then once this goes away, it'll never brighten again. If in addition it has a planet around, you'll get a secondary brightening. Same thing, the planet can also distort light. And here's a little animation I think I got off of Wikipedia, which really displays it quite nicely. Here's the the background star, which you don't actually see the foreground star. That's usually a faint star, but you're watching the background star here, its brightness. And this one has a planet next to it. So you see over a period of about a month or so, this brightening of the background star. And then over a shorter period of time, only a day or two, you get a secondary peak indicating there's a planet there. And folks, so you have to have incredible continuous monitoring in order to catch this little short blip like this. Believe it or not, microlensing has been done from the ground by having large networks of tens of telescopes distributed all the way around the Earth, so that whenever one area goes into the darkness, another telescope picks it up on the other side of the Earth and watches the same star. And they calibrate their photometers precisely so they can actually measure these microlensing events from the ground-based telescopes, which is quite amazing. But WFIRST would have the advantage of actually staring again for long periods of time with the same photometers, no problems with calibration. And what it's expected to be able to do is fill out a lot more of this discovery space plot. Showed you before, this is the masses as a function of how far they are from their stars. The red plots are basically Kepler planets. You can see Kepler found thousands and thousands of transiting planets, not too many like Earth. Here are the Doppler planets, and the black ones are sitting behind there, as well as some direct image planets. And the blue ones are what they think WFIRST microlensing will be able to be sensitive to. Something like these guys here. And I see in the process of changing the slide around, this green box should have been down here, but here are Venus and Earth. And this is what we really would like to see. And so you see microlensing for WFIRST can just kind of barely find things out here. We'll barely be able to see Earth and Venus. We even can find some Mars, as well as some lunar mass type, or outer satellite asteroid masses. But it'll only, if it sees them, they're not going to find very many of them. It should be able to find 1,000 altogether, but maybe just a few of these. But even if it does detect them, that's it. You'll never know anything more about it. You won't even know what the star was like. You're never going to be able to follow up to see if it has an atmosphere, if it could be habitable. All you know is it's roughly, you don't even know exactly the mass. You know the ratio of its mass to the mass of its star. So it's kind of intriguing, but it doesn't really help us looking for Earth-like planets. Okay, but some good things did come out of the since 2006. The Transiting Exoplanet Survey satellite was built and launched. This was a cheapo. It was a mid-X mission for NASA, a mere $200 million. You can see from the size of the telescopes that help keep the cost down. These are only 10.5 centimeter telescopes, 4 of them, sort of fly's eyes, very wide field. And the point was to look at a very wide portion of the sky and look for more transiting planets with high precision photometry. It's on a very odd orbit. Kepler was on an Earth trailing orbit as it went around the sun. This TESS is on an orbit around the Earth, but it's synchronized with the moon. The moon's orbital period is 28 days. TESS has a 14-day orbital period. So I spend 28 days staring at one sector of the sky, and then it tiles the entire sky, or 80% of the sky anyway. It goes slowly, 28 days at a time, looking everywhere. But since it's only staring at for one area for 28 days at a time, if you want to see at least 3 transits to be believable that there's something there, then you can really only see things with periods less than 9 days or something like that. So you're only short period planets. So if they're going to be habitable, that means they have to be really close to a star. And if the star is the sun, you don't want to be that close to the sun. So you have to be around a low mass, very faint star like an M dwarf, like Barnard's star. So the whole point of TESS is then to look at all the M dwarfs all over the sky and see if they've got Earth size, because all you do is measure the size, Earth-sized planets around nearby M dwarfs. And then those would be good targets since they're transiting for James Webb Space Telescope to look at later on. But the best thing is at this point, TESS has found several thousand candidates, and roughly 500 of them or so have been actually confirmed, which means they've been detected by Doppler spectroscopy. A lot of it done by my colleague, Joanne Teskey, using our Carnegie Magellan telescope in Las Campanas. So Carnegie, again, has a very important role in making sure that TESS delivers on exactly what it's finding, not only having the size, but also the mass of the planet, so you can get a density of it. So TESS's role was to prepare for a James Webb Space Telescope. which also did launch successfully just 3 years ago. And it's really great for doing spectroscopy of transiting planets. It has really high spectrometers in the near infrared and mid-infrared regions, sort of 1 to 100 microns. And so it can look for species of interest for habitability, but it's essentially only transiting planets. It's not designed to look for imaging like we talked about with the coronagraphs. And the main problem is it has these 18 hexagonal tiles, each of them with a little edge, which diffract and scatter light, which means if you try to shine starlight off of this, you're going to get all kinds of stuff scattered all over the place. You're never going to find that 1 part in 10 billion signal. Unless you happen to see a big Jupiter way out far from its star in infrared wavelengths, JWST could image those, but it's really mostly to be used for transiting planets. So $11 billion, that still is a good deal, I guess. In the meantime, he says sarcastically, because after all, SIM and TPF, which I worked on, died so that JWST could live. In the meantime, turns out the ground-based folks came up with a system which is really great for JWST to look at, the TRAPPIST system, which is again another low-mass star. So it's only maybe 1/12 the mass of the sun, close by again. And it has a system of at least 7 planets all in the same plane. They're all lined up, so they all transit one after the other. It's just incredible. Who would have thought that nature would leave a system like that pointed right in our direction? And because they could also learn a little bit about how they affect each other's orbits, their timing, through so-called transit timing variations, they can estimate the masses. You can't quite read this very well, but here's the habitable zone going farther out from the stars. This is 0.4 Earth masses, 0.6 Earth masses, 0.7 Earth masses, 1.34 Earth masses. These are what we're looking for, Earth mass planets in the habitable zone. So wow, here we go. All we need to do is have JWST look at the TRAPPIST planets. We'll probably find evidence for a Earth mass planet. Let's see if it has an atmosphere on it. But what are we looking for in terms of atmospheres? The answer appeared in the Washington Post this week, conveniently. And if you watch read Brewster Rocket, certain things to look for if the planet harbors life was methane, CO2, water vapor, organic compounds, and Amazon packages. I know that the Post did not put its usual disclaimer about Amazon and Jeff Bezos. I felt I should write a letter to the editor about this to point this out. But the one thing they're missing was oxygen or ozone. These are sort of the major biomarkers. We can see those elements, compounds in an atmosphere of a planet. We'll say, well, it not only could be habitable, it might actually be inhabited, because in particular, if you can find both methane and ozone, they cannot coexist without having a source of both. If you just have abiotically produced ozone and methane, they will combine and give you water and CO2. So if you've got methane, which on Earth is produced primarily by methanogenic bacteria in swamps and dairy cows doing certain things in their digestive tract, and ozone is produced by photosynthesis. If you have those two sources of methane and ozone, you'll have some sort of a steady state level indicative that your planet has methanogenic bacteria and cows. So I think the American dairy industry should be interested in that finding. So that's what we're looking for. So what did JWST find when it looked at the TRAPPIST system? Put a lot of time into it because everyone knew this is perfect. Let's really study this life out of the system. Well, they did announce recently the first steam atmosphere was found. Well, they were able to do spectroscopy by separating out very carefully the light from the star and from the planet, both during before transits and during eclipses. And they found water. The only problem is that this guy has 2 Earth radii, so it's like 8 times the volume of the Earth, but only 3 Earth masses. So it's like 3/8 the Earth's density. It's not a rocky iron body like our Earth is. Maybe it's more like an ice giant or something. It certainly has water. It's also on a short enough period that it has a very hot surface, so it's a steam world. So interesting, astrophysically interesting. It's worth publishing a paper on, but it's not what we're looking for. It shows JWST can do the job. It's just that when they looked at the TRAPPIST planets, they found nothing so far. bare atmospheres or some sort of cloud layer that doesn't give any hint of what's inside. So JWST is still going to be looking. There's still, those other 500 odd planets that have been found by tests. So perhaps something will come. And again, it'll probably be in the Washington Post when it does appear. But so far, it hasn't happened yet. So what else has happened since 2006? Well, that's long enough ago that we've had yet another decadal survey. Astro 2020 just came out a couple of years ago. Reshuffled the cards because a whole new deck of people come in, and it's you get a whole new set of answers. They finally said, well, maybe we should build a TPFC. Oh yeah, gosh, who would have thought of that? They just gave it a new name, the Habitable Worlds Observatory. It should be 6 meters. Yeah, gosh, I remember 6 meters, something like launch fairings and things. And look at 100 nearby stars. And if we think eta sub Earth is 0.25, we should find 25 Earths. Okay, good, great. It's going to be very expensive, though, we know, after having spent 10 billion or so for Hubble and 11 billion or so for JWST. And they don't have that much money right now to spend on it. So they're saying, let's go into technology development for this. Let's spend 10, 20 years figuring out how to build this thing. And one of the key things you need to do to make this work is, of course, is to have a coronagraph. We talked about before, something more better than just your thumb blocking out the starlight. So one good thing came out of the W first, besides giving microlensing, which nobody ordered. They decided, well, let's put on a coronagraph as a tech demo. I, being cynical at this point, after 32 years of this stuff, I put on the coronagraph so that they can, it's a D-scope option. When they run out of some problem, they don't have enough money, they'll just say, oh, we'll cut off the coronagraph because it's not necessary. Believe it, amazingly, the coronagraph has survived. It even exists. It's been built. And I know it in great detail because I had the honor of serving as the chair of the independent review team that oversaw the development of this instrument for the last 6 years. This is what it looked like this spring before they put the cover on it and put it on a truck and drove it cross country to Goddard. So it's now sitting over at Goddard Space Center, ready to be mated with the rest of the spacecraft, ready for that 2027 launch. What will it do? This is a pretty advanced coronagraph. It has all the hybrid LEO features that we talked about for the TPFC coronagraph. It also has a rather peculiar shaped pupil coronagraph to take care of the fact that the Roman Space Telescope is not really ideal because it has a secondary mirror with 5 struts to it, which you don't really want because that's producing light that scatters and diffracts. You want to have an off-axis secondary, so light comes off the primary, off the secondary of the instrument, so you don't get any extra scattering. We couldn't, that was the way we had to take what NRO gave us, not the ideal telescope. And so there were some creative people who figure out ways to sort of block out those struts from the secondary and do the best they can. So it still is going to be a very successful chronograph, and here's what we hope we'll be able to do. This again is a little bit complicated, but let me show you. Let's see, where is sorry, moved it over here. Here we go. So here's again the contrast. So here's our part in 10 to the 10th, 10 billion for Earth down here, very close to its star. And the plan was, these are functioning telescopes in space like the NICMOS on HST, James Webb Space Telescope, NIRCam. They can kind of get down to the 10 to the minus 7, 10 to the minus 8th regime for contrast, out pretty far from the star. The point was to try to get down in this regime to get closer to where Earth is. This is where we're headed for. This is where Habitable Worlds is going to be heading for. We've got to try to get to this sort of contrast this far in. And so the original plan when W first chronograph was being specified was to be able to reach this level of performance would be considered level 1 requirements passed, but they're hoping to get down here. Now, because they did sort of de-scope it a little bit, they didn't have as much money to spend on it. It was turned out to be like $432 million for the chronograph alone. They declared, moved the goalpost up here and said, listen, if you can get to 10 to the minus 7, we'll declare victory and say, yes, NASA did a great job here. But those of us who have been in the background are saying, that's okay. We're not going to only do that. We're going to go down here. We're shooting for down here. This is what the thing has really been designed to do and not necessarily proven yet. But we think it's going to go down to the 10 to the minus 9th level. So we're going to be within a factor of 10 of what we need to see Earths with habitable worlds when it does fly. Okay, now what about habitable worlds? Well, we don't quite know how it's going to be built. The folks at Goddard really like hexagonal tiles, which, as I pointed out, makes for problems for chronographs. But somehow they think, well, if you can deal with that crazy secondary on Roman, maybe you can deal with hexagonal tiles on this. But this is to be determined. This is literally sort of what an image would look like. It'll be very hard to see Earth. We'd only be able to see it on certain parts of its orbit. If you can block out, null out the starlight in the center, as well as this would be Jupiter and Saturn out there as well, and Venus. That's literally the sort of predicted image what we'll be able to see. So that sounds good, 6 meters or so. As I said, if you fly it on Elon Musk's Starship, you won't have to fold it up like James Webb's was folded in half actually to launch on Ariane. You can just fly the whole thing as is. The only problem is this little number here, 2045. I'm 73, and I'm thinking 94. Maybe I'll make it. I don't know. Gives me a reason to try to stay alive. That's for sure. So it's great for young people. Let's be upbeat. Young people in the room, raise your hand. How many's going to be alive in 2045? The rest of us will just keep quiet. There we go. There's an optimistic person. So that's the plan. But literally, the Goddard office was created just this fall. They're in the process of setting things up and getting the scientists to really get serious about it. Okay. Meanwhile, what else did Astro 2020 do? Well, they also talked about what should be built on the ground. And they finally went for the top ground-based element, the U.S. Extremely Large Telescope Project, which is a combination of the giant Magellan telescope, which Carnegie leads, and the 30-meter telescope, which is led by Caltech, University of California. The only problem is they've got great telescope designs, great plans, but they need more money. So hoping that NSF will pay roughly 1/3 the cost of this combined project. That's a bit of a problem because NSF is just as cash-strapped as NASA is. But our new president, John Mulcahy, just became president of Carnegie Institution from last week. One of the top things he'll be trying to do during his presidency is find some more money or some more partners or help raise this money to build the GMT. So what will GMT do? Here's what it'll look like, by the way. This is, of course, the artist's conception of what it will look like on top of our observatory, Las Campanas. This is actually, of course, the Milky Way galaxy. And if you know the southern sky well, that's actually the Large Magellan Cloud over there. Will be gorgeous. You'll notice it's not a traditional simple dome building. They've gotten beyond that to more rectilinear designs with holes in the side to let the air pass through to remove something called dome seeing, where you have atmospheric currents just because your dome is cooling it all night long. You want to be able to cool down to the night temperature right away to reduce the effects of seeing. So what will GMT do in terms of exoplanets? Well, if you go on the GMT website and say, what are you going to do with this thing? Well, the number one thing is find Earth-like planets and search for signs of life. Well, okay, yeah, that sounds pretty good. But how are you going to do that? Well, turns out that we know right away the best target to look for right away. One of our postdocs, Guillaume Anglade-Escudé, ran a long-term radial velocity survey on this little star here, Proxen B, Proxen, I should say. It's a member of the Alpha Cen system. Alpha Cen is a binary star system, so 3 of these are seemingly close by. This is actually the closest star to the Earth. So they went 1.4 parsecs away. Alpha Cen is just essentially the same distance. 4.3 light years. So this guy here, Proxen, is again a low mass star, a red dwarf. And Guillaume Anglade-Escudé found was able to spend a lot of RV time on this, radial velocity time, and found evidence for a 1.3 Earth mass planet on an 11-day orbital period, which is the habitable zone for this low mass star. And hey, that's just what we want. We know it's there with the right mass. It's in the habitable zone. The question is, does it have an atmosphere? Just like we look for TRAPPIST, failed, find something. What's the atmosphere on this guy here? Well, unfortunately, you can't use JWST to do it because Proxen B doesn't transit. It's just a normal planet out by itself. So in order to get its atmosphere and actually take a picture of it, you have to do the hard thing of direct imaging. No transits. People hope for a transit. There's no transit seen to date. So how are you going to do that? Well, all you need is a GMT, because it turns out Proxen b, even though it's sort of the same brightness as the Earth, it's next to a star which is not as bright as the sun. So instead of having to have 10 to the minus 10 billion contrast, you only need to have 10 million contrast to be able to see it. It's somewhere up in this area here. This is sort of a guess about what might be out there. There's stars or actually crosses or known planets. GMT is large enough that it can come close enough in to pick out Proxen b from its host star. W first, being only 2.4 meters in size, can't resolve it. GMT is 25 meters in diameter. It's 10 times bigger. It can do Proxen b. All right, there you go. Now, in addition, they expect to be able to see on maybe another 100 or so planets. This is a chart of the known planets that are accessible for the GMT. This one down here, the big circle, is Proxen b. Yes, that is going to be one of the key targets. What they have to do, though, is build something called GMAG AOX. This is a new version of the same adaptive optics instrument that's on the Magellan telescopes now that Alicia Weinberger uses quite a lot. She was just in Chile last week for an observing run. You have to do something called adaptive optics because we're now on the ground looking through the atmosphere. It'd be nice to take this to space, but even Starship can't take this thing to space, 25 meters. So you have to have adaptive optics, which very carefully corrects for distortions of your wavefront as it passes through the atmosphere. You have to have a whole lot of mirrors that correct and change for that waviness of the distorted by the Earth's atmosphere. So this is the GMT Magellan adaptive optics extreme version that is being planned for the GMT. They know how to build it. They've got papers published how to do it. They've proven that it works. It's using a chronograph that Olivier Guillaume, who won a MacArthur Award long ago, designed, and has been using on the Subaru telescopes. The main problem, again, is, guess what? Money. But they know how to build it, and they're just waiting for some money to come along and build this first light instrument for GMT. Another great thing the GMT will have is something called the GCLEF, the GMT Consortium Large Earth Finder, which will be a much improved so-called extreme precision radial velocity instrument, being advanced beyond the planet finding spectrometer that our colleagues at the Carnegie Observatories and Paul Butler built for our Magellan telescopes, which can kind of really only do things at sort of 1 meter per second or so, which means you're limited to seeing planets around lower mass stars in the habitable zone again here. With GCLEF, you'll be able to find up to Earth, because you need to be 8 centimeters per second. Earth's wobble is like 9 centimeters per second. GCLEF will get you in the regime where you can actually find brand new planets that could be looked at with the AO system, but you have to find them in the first place. And so GCLEF will be important for finding them. And even possibly if they're bright enough, they might be able to do some spectroscopic tricks to learn something about the atmospheres while doing Doppler velocity at the same time. Okay, we're getting close to the end. Here's what GMT hopefully will look like for first light in the 2030s. 2030s is still pretty far up, and it's not 2045 like Habitable Worlds. This is basically what the mountain looks like now, except for the fact that this doesn't exist. That's obviously our conception, but they've blown off the top of the mountain. I was actually still down there observing when we were told at 12 noon, let's go outside and watch the blasts on top of Las Campanas itself. And they blow off some rock, and then they go out and clear it away. So they leveled the mountaintop. You can't see it, but behind this dome here is the ridge that streaks back to the Magellan telescopes and the DuPont telescope on the far end. So this stuff is completed, and they're already beginning to design and build this the mirror support structure. This thing here is being designed right now and built. There's a large building that's built by the manufacturer to house that structure. Of the 7 mirrors that are in the primary telescope, 7 of them they've all been built. 3 of them have been polished and are figured and are ready to go. 4 of them are still in the process. So they're making great progress in getting the mirrors ready. So, okay, that's where we are as of 2024. So here's conclusions part 1. Here's again that discovery space plot, sort of what I showed you earlier on, but now with thousands more planets on it. So many, they all overlap each other. Found by radial velocity, by transits. But there's still nothing quite down here where Earth and Venus are. That's because we have to get habitable worlds or G-clef or somebody to push us down into this region down here. But we do have Earth massish planets over here on short period orbits, and if they're around M dwarfs, then they're going to be habitable, like the ones I just showed you about. So we have some more targets. We just don't know if they're going to show evidence of atmospheric stuff that are of interest for us. And there's a sort of blow up of that. Here is Proxen b, which I told you about. Here's Earth and Venus over here, roughly the same right mass, habitable zone, 11-day period for this star. There's also at least another planet in the system, Proxen d. There's actually Proxima c, which is people are arguing about, but these two are accepted. And even more interestingly, guess what else is here? Barnard b. Remember we started? Peter Van de Kamp? If he'd only continued taking data for another 50 years, maybe he would have found, no way he could have seen this. But that is really amazing that after all these years, turns out Barnard star, again, the closest star to us, has probably a hot Earth-like planet. Probably not going to be habitable, but there might be something else in that system too. So that's where we are. 18 years later from where we are, we made tremendous progress, but there's still a lot more to be done. And largely at this point depends on the will to build these telescopes, build them correctly, and get them to work. And especially it's incumbent on Carnegie to make sure we get the GMT built for future work for us. So at this point, I'll stop and thank you all for your attention.
Thank you so much, Alan. Okay, I will take a few questions. Who's got a question? Here's the.
Yes, I'm glad you are astrophysics because I have friends that get involved in these discussions. What is your theory about UFOs? Are they really extraterrestrial? It's just a myth. What are they?
I think there are a lot of unidentified aerial phenomena which people, sober people have found that they have no explanation for. Again, our trustee, David Spergel, was in charge of the NASA-appointed panel to look at all this information and gather it. And a lot of things could be explained by strange things, weather balloons or secret aircraft, even our own secret aircraft doing strange maneuvers that people didn't think were possible. There's still some residual number of phenomena that are not explained, which means really people should continue to look for these things and whenever possible, take as much data as possible. And especially if a scientist involved, nothing would make a scientist happier than to find an alien spacecraft. My goodness, think of the grant money you could get for that, right? I mean, boy, you might even get a Nobel Prize. And they might have to share it with the alien, though, I suppose. So you only get $500,000, but it should be taken seriously. But I don't believe there's anything that at this point is definitive to make me believe that intelligent beings have come to visit us. What I think is more likely is that by looking for these sorts of things where we're looking for probably planets with microbes, methanogenic bacteria, not necessarily dairy cows, but methanogenic bacteria is what we're probably going to find first, because intelligent life has only been on this planet for a short period of time, and multicellular life for 500 million years. And if a planet's 5 billion years old, there's sort of only a window in time when we're around. That makes it that much harder to find intelligent life on the nearby world. So we're probably going to find microbial life. If we find that, I think that will be a tremendous advance.
Would they even go as far as saying that NASA knows what they are hiding?
No, I don't believe that at all, because NASA cannot keep us. They can't keep a secret. They really can't. I know these people. They would be saying they were. You couldn't sit on that one. That's too important. Really, I'm being serious. It really is too important. You cannot hide that.
You're looking for Earth-sized planets and Earth-sized planets near stars that are similar to our sun, I presume, and then assuming that has a higher likelihood of having life. What about larger planets or smaller planets? Would would there be conditions for life on those planets as well?
Of course, we don't know. We have to just sort of look under the lampposts to see where we think we can find life similar to our own. I mean, Carl Sagan at one point thought there might be life in the atmosphere of Jupiter floating around up and down. So people can be very creative about other forms of life. But certainly, I mean, these M-dwarf planets, they're Earth-sized, but they're around a different type of star from ours, which means you have the other challenges because M-dwarfs tend to emit a lot of high-energy radiation, which may not be good for life. There are many variables. I presented a very simple picture here today. This is a very active area of research for everyone, but certainly we could very well be surprised. Certainly microbial life, I would imagine, could evolve on planets with, very different degrees of gravity. Maybe everyone will walk around with rhinoceros type legs because the gravity is so strong there. Who knows what would happen? But we have to sort of start with, can we at least find life as we know it? And maybe along the way, we'll stumble across something else. We stumbled across hot Jupiters. Paul Butler did not bother analyzing his 10 years of data because he thought we don't have 12 years of data to find Jupiter yet. After 51 Peg was found with a 4.23 day period, Paul Butler looked at his data and found right away some planets because he knew what to look for now.
Yeah, so thanks for the talk. You already got the obligatory question about UFOs, so I won't ask that. But I am curious about if we flip that question around, and you presented a variable called Eta Earth. Is there a similar variable for the probability that we have been observed as a habitable planet by some being on a different planet or in a different solar system?
Yeah,
And
as
what
far
would
as
it
I
be?
know, there's no Greek letter chosen for that. But
Right.
Actually, I think the easiest way for someone to detect us, besides looking for I Love Lucy going through the radio waves, but it's actually the early warning radars, which were active in the Northern Hemisphere looking for Soviet ICBMs, which blasted a lot of radiation out in certain directions of space. And I claim, that stuff's going out at the speed of light. So if you happen to be in the direction of one of those radars, they would say, what in the world is that? And then it just shut off because, Gorbachev took over. So there are things we emit radiation, and we have some interesting things at times in our atmosphere, like the CFCs that we were coming out of air conditioning units. That would be a clear sign of maybe it's intelligent life, maybe it's not intelligent life. But there are things that people can find about us, but there's no, at least I don't know that anyone's done a serious study to try to estimate that, because folded into that is what's the chance that that star has life itself. So it's the same problem in a sense.
My question has to do with your allusion to money and how that plays into, it's a limiter, right? So I was just curious, in some things that affect us humans, we don't know for sure, like with curing cancer and how much money can you put into it to get some desired results. So do you think the confidence of, you were saying, oh, we know how to build this stuff. Do you think it really is a sort of just a matter of money and not more discovery of technology and how to see with all the different light waves and things? How would you characterize the confidence in knowing that we could do it if we were willing to pay for it?
Yeah, I happen to, Michael didn't mention this, but for the last 10, 15 years, I've also been chair of NASA's Exoplanet Exploration Technology Assessment Group, where we go through and assess all the progress that's been made in building things like coronagraphs. And so NASA has a very specific scale called the technology readiness level, which basically TRL1 means you had a drink with somebody and drew something on a cocktail napkin. And 10 means it's flown several times and always worked. And technology readiness level 5 means, wow, we really got all the bugs out of this. We basically built a full-scale model of this and in the lab and shown it works. And now we're ready to go ahead and cut metal and send one into space. And I didn't talk about it in this talk, but there's yet another concept for imaging nearby Earths, which is not an internal chronograph, but an exterior star shield. Instead of having the moon, you have a very elegantly designed hypergeometric flower design, which bends the light that would normally come towards you and shoots it off at other angles. The Star Shield actually just passed to TRL5 a couple of weeks ago. And again, I chaired the committee, signed off on that. Yes, it's good to go. So we're ready for Astro 2030 to say, hey, why don't we fly a star shade, a mere $1.2 billion, and that will actually do better than these internal chronographs I showed. It'll actually achieve maybe another factor of 10 better contrast. So the point is that NASA has a very particular process. They've been in this business a long time, longer than I've been in it, and they know how to march things through, very carefully testing it all along the way, and you do not get permission to go ahead and fly until you've shown that you can actually build this, because they don't want to waste any money. They do not want to have egg on their face. They're not like Elon Musk, who doesn't mind if it blows up the launch pad. They don't want to do that. They want everything to be a success.
Got 2 more, 3 more? Or do you want to keep going? Okay.
Yeah, great. Are there aesthetic or appearance considerations in designing the GMT or others? And when did the transition from domed observatories to boxy types like this or the MMT?
Well, I know on Las Campanas, we have the DuPont telescope, which was built around 1976 or so. It's a classic dome. Magellans were designed, Alicia helped me with this, early 1990s, Magellans.
Yeah, finally commissioned 2000.
Okay, and so the Magellans have this boxy design. So somewhere between 76 and 1990 or so, people realized we don't want this closed dome. We want something nice and airy. We can open up louvers on the side and get rid of dome seeing. It really is, dome seeing is the big thing. You want to equilibrate with the nighttime temperature. Now it gets hot in top of a mountain in Chile in the summer, at least during the daytime it gets hot. So you close everything up, and then as soon as it starts getting dusk, you run the telescope, open everything up, and hope to cool down.
But not cost considerations, because boxy seems like much cheaper to build than a dome.
I think that the amount of money we're talking about, whether or not it's a shaped steel plate or a slab of steel, I don't think it's an important thing, because in the end, you want performance. If you're spending, Magellan was 70 million altogether. So if you worry about a couple $1 million on the design and it doesn't work very well, what's the point of building it? So in the end, you go for that which works the best. If you can't afford that, then you wait until you get the money to build it, which is where we are in GMT. We know how to build it. They're building a lot of it, but they're waiting for it to get a bit more money to finish it.
You know, a couple of times you mentioned that you didn't like the hexagonal tiles. A couple of times you mentioned you didn't like the hexagonal tiles in JWST. What shape would you favor, and what would the trade-off be to get the less diffraction if you then used the shape that you're talking about?
Well, actually, people who at JPL who are working on designing chronographs could see that the Goddard Space folks who like hexagonals for some odd reason since they built JW, they've been trying to figure out how to build a chronograph to take care of the hexagonal tiling. So they think they can do it perhaps. But the ideal thing would be simply a monolith with no edges, with an off-axis secondary. And then all you have is the edge and a simple monolith, parabolic figure. And then all you worry about is the starlight. You don't have to worry about diffraction inside your telescope.
Okay,
Yeah,
here's the mic.
last question.
Here's your-
So,
Wait, here's the microphone.
thank you. With present instrumentation, is it possible to detect biosignatures in the atmosphere of super Earths, assuming they're in a habitable zone?
Yeah, yes. I mean, the one slide I showed you of JWST showing that steam world, that proves the case.
Yeah.
You know, they can do it. This JWST has wonderful infrared, near-infrared instruments. They can do the job, just have the right target.
But this search is continuing.
Oh, absolutely. I mean,
Yes.
other people in this room, that's
Thank
why
you.
many of our postdocs are up to their ears doing this sort of work right now. Whenever they give a talk, I don't even know what they're talking about because they're so much into it. They really know what's going on. It's a new thing for me every time I go to a postdoc seminar, but several, 3 or 4 postdocs in our group here are avidly trying to figure out what JWST can do with test targets.
Well, thank you so much, Alan.